We're now going to turn our attention from infinite sequences that we've been working with to the idea of the infinite series. An infinite series is simply the sum of an infinite set of numbers. It's kind of like the sum of the sequence. So instead of a list of numbers, A, B, or A1, A2, A3, etc., we're now going to have a sum of numbers. And again, I really want to emphasize this. The sequence is the list. A1, A2, A3, A4, etc. And we often simply say it's a set of terms, A sub n. The series is what happens when we add all those terms up. Because we're adding, we can use that sum notation that we learned back in Calc 1, right? We often write a series using summation notation as the sum as n goes from potentially 1 to infinity, although we could start with other n values as well, of each of the terms A sub n. One of the most, I don't want to say it's really challenging, but it's just easy to forget. One of the things you really want to keep in mind as you go forward with this chapter is to ask yourself, am I working with a sequence or am I working with a series? The things we've talked about before, the tests that we've used, like those growth rate tests or the test for the geometric sequence, things like that. Those are all sequence tests. They do not apply to series. We're going to learn a whole new set of tests to test for the convergence of a series. And you really want to keep those separate in your mind, because that's the most common mistake that I see going forward, is using a sequence test when you should be using a series test, or vice versa. So, we're going to begin in this particular video with a fairly informal introduction to infinite series, and then the remainder of the chapter will begin to talk formally about all of the convergence and divergence tests that we'll use to decide whether this sum converges to a finite value or diverges, in other words, goes to infinity. One of the questions that may be in your mind is, how is it even possible to add up infinitely many things and get a finite value as a limit? I'm going to show you this visually first. Again, this is a little bit informal, but there's a really nice illustration. I've taken this right from your textbook. It's in there as well. That really shows well how we can sum up infinitely many terms and get a finite answer. Let's imagine a whole square. It's a 1 by 1 square. And so the area, 1 times 1, is 1. What we're going to do to create our series is we're going to start adding up pieces of that square. I'm going to begin by taking my whole square, cutting it in half. And so my first sum, which I'm labeling S1, is just this shaded area, 1/2. To progress, I take the unshaded area, cut it in half, and add that new area. So I still have the 1/2 that we started with, and now I'm adding 1/2 of a half, or a 1/4. That sum I'm calling my second sum, or S2. We'll continue to do this. Notice down here we have our third sum. We have the 1/2, we have the 1/4, and then we have 1/2 of the previously unshaded area. 1/2 of a 1/4 would be 1/8. And so the total shaded area now, 1/2 plus 1/4 plus 1/8. We can continue to do this. There's 2 more progressions shown here. If we go up to here, here we have that previous one, the 1/2, the 1/4, and the 1/8. And this time, we're going to take this previously unshaded area, cut it in half, and add that in. That would be 1/2 of 1/8, or a 1/16. And it gets too small for you to even label, but you can see they've kind of completed more and more and more steps, always adding in 1/2 of the previous unshaded area. They've also identified a pattern at this stage. Notice that in these fractions, while the numerator remains 1 every single time, these denominators are just powers of 2. 2 to the first, 2 to the second, 2 to the third, and 2 to the fourth. So when they try to sort of indicate this infinite progression, they've used that pattern to say any term s sub n, if I want to sum up n terms of this series, we'll start with this 1/2 plus 1/4, etc. And we'll keep on going through 1/2 to the n power. Now what happens to this sum if we let the value of n approach infinity? As we let n become an infinite number of terms, I'm adding up an infinite number of fractions. What does the sum approach? Well, if you look at the total shaded area inside that square, we're getting closer and closer to the total area of the square, right? We're missing just this little tiny piece now, and we would be missing less and less the more pieces we added on. So, since the original area of the whole square was 1, this area is approaching 1, and that means that this sum approaches 1 as well. So visually, there's an example of a sum of infinitely many terms that still has a finite sum limit. All right. There's actually another important idea that was illustrated in that example. The diagram, of course, showed the additional pieces being added to the area and then additional terms being added to the sum as we went. And the resulting values we labeled with these subscripts. S1 was not really even the sum, it was just the first term, right? S2 was the sum of the first 2 terms. S3 was the sum of the first 3 terms, and so on, through Sn, which would be the sum of the first n terms. These numbers, the S1 through Sn, if I were to write them as a list, as a sequence, form what we call the sequence of partial sums. What's nice about forming the sequence of partial sums is we already know how to test a sequence for convergence. If the sequence of partial sums converges to a particular value, then the sum itself will also converge to that value. If the sequence of partial sums diverges, then the infinite series diverges. So what we're really saying here is if I wanted to sum, let's say as n goes from 1 to infinity, these S sub n's, that series sum is the same as the limit as n goes to infinity of the sequence of partial sums. So again, really nice here. We've got a way of summing a series by looking at a limit of a sequence, which we already know how to do a lot of things with. Let's look, and I'm going to continue with this example for now. And by the way, this is one more section where I'm having to redo the video, so I do have some stuff written out. This is the last one. After this, you'll get fresh videos again. All right, so let's take a look at this sequence of partial sums for our problem. Right? The first shaded area was just a half. The second shaded area was a half plus a fourth, right? And I'm just using all these values right from here. And then we had the third one, the first 3 terms, 4 terms, 5 terms, and so on. And either just in your head or with a calculator, of course, you can easily add up those fractions. The second partial sum adds up to 3/4. The third one to 7/8. The fourth sum adds to 15/16. And the fifth sum to 31/32. So if I'm going to form my sequence of partial sums, I'm just taking all those sums and putting them in a list or sequence. We can fairly easily guess a formula for that sequence. We had already noticed that the denominators were powers of 2. So notice I still have the 2 to the n in the denominator. And then in every case, the numerator is exactly 1 less than the denominator. So the numerator would be 2 to the n minus 1. To find the sum of the series now, we know we can do that because of that last little box on the previous page by taking the limit of this sequence of partial sums. And since I was able to write a formula for it, I can use math that we already know. As n goes to infinity, this is certainly an infinity over infinity case. L'Hopital's rule not so useful here because the derivatives of the 2 to the n's is just going to keep having 2 to the n's in them. So instead, I'm going to use the idea of breaking this fraction into 2 parts. 2 to the n over 2 to the n minus 1 over 2 to the n. Of course, 2 to the n over 2 to the n is 1. And this becomes 1 over infinity, which would be 0. So I have 1 minus 0, and I do get the limit of 1. We expected that based on the visual, but now we can see it analytically as well. Since the sequence of partial sums converges to 1, this tells me that the series sum of 1 over 2 to the n, as n goes from 1 to infinity, also converges to 1. If the sequence of partial sums converges, then the series also converges. And to the same value, which is pretty awesome. All right, in our next example, we're going to look at, I'm going to say it's an application. It is a mathematical application. It's not so much a real-world application, but it's probably something that you've seen before, and it kind of explains some interesting math. At least I think so. We're going to look at the series 0.6 plus 0.06 plus 0.006 and so on. We're going to try and write that as an infinite series using summation notation. We're going to write out the first 5 terms of our sequence of partial sums, and then kind of just by inspection for now, we're going to draw a conclusion about the convergence or divergence of the series. So here we go. I've just simply written out the sum right here, and I'm going to notice that to go from one term to the next, we're always multiplying by a tenth. Right? We're moving the decimal left 1 every time. So that's basically multiplying by a tenth, or 0.1. So that kind of gives me a hint how to write this series. Each term, starting with the 0.6, then gets multiplied by an extra factor of 0.1. The first 0.6 has 0 factors of 0.1. The second 0.6 I've now multiplied by the first power of 0.1. By the third term, I've multiplied by 2 0.1s, so that would be the k equal 2, and so on. This is really a common form that you'll see a lot. A first term with then a constant multiplier to lead to more terms. And this is a pattern you can use every time. The first term is kind of like the multiplier, the a, and then the constant multiplier is what's getting raised to the power, where we have more and more of them as k gets larger and larger. So, ultimately, I would like to find the limit then of this series to determine what this infinite sum is. I'm going to begin to write the sequence of partial sums. S1 is just 0.6. S2 is the sum of the first 2 terms. 0.6 plus 0.06, or 0.66. S3, we're adding the first three terms, getting 0.666. You're already seeing the pattern, I'm sure. S4, we add the first four terms, 0.6666. And there's S5. I've now added 5 terms, and I've got 0.66666. All right, just by inspection, right? I'm not going to do any actual math here. I'm just going to look at that and say, what's happening? What do you think S sub n is tending towards? And certainly it seems like if I had infinitely many terms, I would just have 0.6 repeating infinitely many times. So I'm saying S sub n is approaching 0.6 repeating, and I probably should have added as n goes to infinity. Well, we know then if the sequence of partial sums is approaching 0.6 repeating, that means that the sum of the series itself is also equal to 0.6 repeating. And 0.6 repeating, you probably already know this, but it's 2/3, right? So the sum of that series is 2/3. So this is looking at a repeating decimal as an infinite series. Let's look at one more. In example 9 here, my series is -1 to the k times k. So over here I've just written out a few terms, right? When k is 1, -1 to the first is -1 times the k value 1, plus when k is 2, -1 squared would be a +1 times our k value of 2. For k equals 3, it becomes negative again, times the 3. For k is 4, it's positive again, times the 4, and so on. You can see we kind of get this alternating effect going on here. Once again, we're going to write out the first 5 terms of the sequence of partial sums. And then by inspection, no real math, just by looking at it, we'd like to draw a conclusion about the convergence or divergence of the series. So here we go. S1 is just that first term, -1 times 1, or -1. S2, I've added the -1 plus the 2 to get 1. Here's S3, -1 plus 2 minus 3 adds up to -2. Here's S4, -1 plus 2 minus 3 plus 4, all adds up to +2. And there's S5, same sum with a -5 added to it, adds up to -3. Now, unlike the previous one, although I see a pattern, right? In fact, I think probably the next one will be a +3. This pattern is not getting closer and closer to a single value. In fact, these numbers are getting further and further apart, right? If I were to just sort of imagine, I start at n equals 1, down here at -1. When n is 2, I'm at +1. When n is 3, I'm at -2. When n is 4, I'm at +2. Then down to -3, right? These are spreading apart, not getting closer and closer together. So when I write down that sequence of partial sums, kind of visualize it this way, I can see that that sequence of partial sums definitely diverges. Since the sequence of partial sums diverges, I can conclude that that original infinite series also diverges. All right, That brings us to the end of our little introduction to series. We'll begin to get some more mathematical types of things that we don't just kind of look at and guess what's happening, but we can actually prove mathematically when we continue in the next video.